I hate sitting here because some of y'all are blocked and I can't see you, but okay, all right. Are there any direct questions before I get started? Because I have to stop at 4:30, and I want to make sure I get to everything that y'all need to know today. So anything in specific that you need to know in today's session, or just kind of generals on making sure you know what's going on in class right now? All right. Okay. So first of all, I have on this worksheet, I have this little table that shows some equivalence between, how we're going to do things in the phasor domain, which is what this first chapter is about. So if we look at do I have Circuits 2 Spring 2025? Oh, that was the first session. What's today, the 6th? Doesn't appear to be pasting. Why is it not pasting? Okay, I give up. I'll just leave it here. Okay, so if we're trying to see how to convert something from the time domain to the phasor domain, then we have these conversions right here. In particular, resistance is real, and resistance is always real. Resistance is just going to be R. Resistance is not going to change. But inductors and capacitors are going to change. So if I have a circuit, and I have a resistor, and I have a capacitor, and I have an inductor, and I want to change this to the phasor domain. So this is originally R and C and L. Then the way I change it is I'm going to take whatever this voltage is as a function, and I'll change it to a phasor. And so, for example, if I had my voltage was 20 cosine 10 pi minus 60 degrees, then as a phasor, that becomes V equals 20 angle negative 60 degrees. I should have had a T in here, 10 pi T. And this 10 pi is the frequency of my circuit. It's the angular frequency, omega, and that would be 10 pi. Now, omega is related to frequency, where omega is 2 pi times the frequency. So you want to be aware of that, because it can trip you up on a test if it says the frequency of the circuit is 60 hertz, and you start working it with omega equaling 60, that's not going to be correct. If the frequency is 60 hertz, if it's given to you in hertz, then the omega that you need is going to be 60 times 2 pi, or 120 pi, whatever number that is, radians per second instead of hertz. So that's the relationship between omega and frequency. So you change the V, the voltage, to a phasor. So you do that first. the resistance is always just going to be R. It's going to stay the same, so you don't have to worry about that. The capacitance is going to be minus J over omega C. Now, you might be, at this point, it might be the first time you've seen this J, and it's probably been showing up in class, and some of you at this point are like, what is this J? Make it go away. Now, unfortunately, it's not going away. It's the same thing that you saw in your high school math class, but you would have referred to it as I. So in math, they call it I, the imaginary unit, the square root of -1. In engineering, you use J as a square root of -1 because I is current. And so if we start using I everywhere, that's going to be a problem. And so we use J as a square root of -1, and that's what that is. So it's a complex number. So when I have 5 minus J2, that's what you would have written in your high school math class as 5 minus 2I. And your calculator is still going to have I. So on the TI-36, which is the one that I recommend, TI-36X Pro, you'll see a button on the left-hand side that has pi, E, and I, and if you press it 3 times, you get I, and that's J. And so if that really is J, then if I square it, I should get -1. And sure enough, I do, and it puts it in rectangular form for me. You might have to, on your calculator, if you use this calculator, it might be set to real, to where if you tried to use an imaginary number, it would just give you an error. But you can also set it to rectangular, which I like, or you can set it to polar, which it'll be like in the phasor form. And so you can set it any of those ways in the mode. Okay, so the capacitance, you can change that to minus J over omega C. And omega, you get that, it's either given or you get it from the function right here. And L is J omega L. And you might notice that the capacitance is negative and imaginary, and the inductance, it's not really the capacitance or the inductance, and we'll talk about the real terms in a minute, but they're in reactance really. The inductance is positive and imaginary, and just keep that in mind whenever you are converting them. If you are finding the impedance, which is the general term for this, if you're finding the impedance for the capacitance, it should be negative and imaginary, and for an inductance, it should be positive and imaginary, and the R is going to be the real part. Okay, so this is going back to this. So this is Z. Z is taking our resistance and our inductance and our capacitance and putting it in phasor form, and Z is called an impedance. So these are all impedances. And if you look at these bottom graphs here, it shows that a direct current doesn't have a frequency. It's not oscillating. And so you're not going to have any frequency response. So frequency response is how does the current change with different frequencies. And so, okay, this time it pasted, but it won't let me move it. It'll let me move everything else. No, won't let me move it. Oh, I don't need that. Okay, so if I look at a graph of the impedance from a resistor, Resistor's real, and it just is a number. So it does not change as the frequency gets bigger. If I look at a graph of the impedance from an inductor, now I have those absolute value signs on there. That means the magnitude of it, the size of it, and that makes it a real number. So if I look at the size of it, and so that just gets the real part. So omega L, since the inductance is j omega L, if I make it real, I get omega L, and as the frequency gets bigger, this impedance gets bigger. But for capacitance, if I look at the impedance for capacitance, as the frequency gets bigger, the impedance gets smaller. So what this means is for high frequencies, the inductor is going to act as an open circuit, because for high frequencies, so if we look at our graphs, for a high frequency, the inductor has very high impedance. Think of it as high resistance. So high frequency is high resistance. That'll put a break in it. So for high frequency, it'll act as an open circuit. But a capacitor for high frequency, the impedance goes down to 0. So it doesn't block the current at all. So for high frequencies, it'll act as a short circuit. And then it's vice versa for low frequencies. So for low frequencies, the inductor is going to act as a short circuit because there's no impedance there, but the capacitor is going to act as an open circuit for low frequencies, which makes sense if you remember when you learned, that after a long time, you learned that an inductor acted like a short circuit and a capacitor acted like an open circuit. That is what they act like at the beginning, and then at low frequencies, because DC is 0 frequency. Okay, now let's talk about what these terms mean. So let's get these terms. And I remember on the first test, he used, you almost always just use impedance in class, but he talked about susceptance or admittance or something that people weren't familiar with, but they're real easy. So we just want to make sure we know what these are. So this is, impedance is the does anybody want to give me their definition of impedance? Because I don't know if I like mine. Opposition that a circuit offers to a flow of alternating current combines, I'll say it combines resistance and reactance. Now, resistance you're very familiar with from circuits 1. What did resistance do?
Opposed the flow of current?
Yeah, especially the flow of direct current. And what reactance really does is it opposes a change in current. And alternating current is obviously alternating, going back and forth. And so if you're opposing a change in current, then that is also going to oppose the flow of alternating current. So we have in inductance, the symbol is Z, and we say Z equals R plus JX. So R is the resistance and X is the reactance. So resistance, you know resistance, it's opposition to a flow of DC current. Oh, by the way, this is impedance is measured in ohms, just like resistance. So resistance is opposition to a flow of DC current. Doesn't depend on the frequency. Hello. And reactance is opposition to a change in current in an AC circuit. It can be positive, which we call inductive reactance. Can be positive. Or negative, which we call capacitive reactance. And it's also just measured in ohms. So I'm not going to do inductive impedance and capacitive impedance because those are pretty much just the reactance from an inductor and the reactance from a capacitor, and we've already talked about inductance being positive, capacitance being negative. So you can fill those in. And then admittance, the last three are reciprocals of the first ones. So, by the way, reactance, the symbol for that is a capital X. So admittance, the symbol for admittance is a capital Y. And it's the opposite of impedance, or not opposite, inverse of impedance. And Y equals G plus JB. So just like X equaled R plus J, Z, so impedance Z equaled R plus JX, admittance is Y equals G plus JB. So when I say inverse of impedance, that I mean 1 over Z. And conductance, and these all, just like reactance and resistance and impedance are all measured in ohms, admittance, conductance, and susceptance are all measured in the same unit. Do y'all remember that unit? No, this one is, the unit is Siemens. And you will find that if you take enough, and that's a capital S is the symbol, you take enough EE classes, you'll find that there are some instructors who really like to use conductance instead of resistance. So conductance is the reciprocal. It says inverse, but I think I'll say reciprocal. Reciprocal of resistance, which makes sense. If R is resisting, if you take the reciprocal of it, it's conducting, and its symbol is G. And susceptance is the reciprocal of reactance, and the symbol is B. Okay, any questions? Okay, so I'm going to stop this recording.